Hello everyone, good morning. I'm Nan, and I'm here with my amazing team members, Christina and Susie. And today we're gonna give a presentation about Google Maps and the data structures behind it. Okay, first, let's imagine a use case of Google Maps. If you are going somewhere you don't really know, you'll probably ask Google Maps, and the map will return you this location. And after some really magic and rapid calculations, it will show you the best route to this destination. So what do we really refer to when we say best route? Do we mean the path which cost fewer time or the one with shortest distance? There are a lot of options, and that depends on users' choices. So, being given what's about, we do have some requirements on Google Maps data structure. First, this data structure should allow you to easily search any location in this map, and you can easily pick any location, or we can say any data, any content in this map. And what's more important, all this data should be interconnected, and these connections should be able to be measured. And as we said, there are a lot of criteria of best route, so this connection should also be able to be weighted. And being given all of this, we get a conclusion. Maybe graph data structure is the best choice for Google Maps. So in this presentation, we're going to talk about what is graph and how it's applied to Google Maps. And we're also going to give a simple explanation of Google's algorithm, which is called Dijkstra's algorithm. And we're going to talk about why graph is the best data structure for Google Map and why others are not. And in the end, we're going to also give a discussion part about Google Maps.
Okay, so a description of the graph data structure. Essentially, it's just a collection of objects that are interconnected, basically a representation of a network. We don't know, but we can tell that Google probably uses weighted graphs, where each node is an intersection, road stop, building, etc., and edges between those nodes have some kind of weight or cost, which could be distance, time, or capacity of transport. And in order to use that information, you sum up the edges for a particular route and see which route sums the least. In order to represent the graphs in the programming language, one of the ways to use it is through agency lists, which are basically an array of linked lists. And within those arrays, each index represents a node. And in those indexes, the elements for them in the linked list are a collection of neighboring edges to the node. An additional field to the linked list could be cost or weight. So application to Google Maps. Obviously, we don't know what Google Maps uses. It's not public, but we can tell that it's just one of the ways to figure out the shortest path problem. And one of the people who tried to solve this problem was Dijkstra, a computer scientist, and he came up with his algorithm, which is basically starting from a starting node, visit the neighboring nodes with the smallest cost, and then whichever one has the smallest cost, visit those neighbors and continue finding the whichever neighbor has the smallest cost, summing for each route. And if we find a smaller cost, update to that route. Essentially, it's just making decisions off of immediate optimal choices. But however, we know that maps have loads of information, data, nodes. So Dijkstra's algorithm is not good due to the nature of maps. There's constant information that's overflowing, and trying to figure out the optimal route each time is not good. is not efficient. So Google algorithms is most likely a lot more complicated. So why did we choose a graph? Well, the Google Maps, there's essentially a lot of paths and directions based upon connections. There's a starting point, end point, and these routes overlap and cause other points to be used. There's no hierarchical structure to the data points. No one data point is there's no order to the data points. There's a multitude of ways the points can be interconnected, and graphs allow us the flexibility to do all of these things.
And I will talk about why other data structures is not as ideal as graph. First, array is the simplest and most widely used data structure. And since it's linear, it's not suitable for representing maps. When it's representing in one-dimensional, it's really hard to display the distance and calculate travel time. Even when it could be represented in multi-dimensional arrays, it's still hard to show the exact location since the arrays are still limited. And the stack is a derivation from the array. It is also linear, and the last in first out rule limited it to find the location. And it's really hard to display distance too. And the queue is another linear data structure. It's dynamic and it's hard to display distance from queue since it's first in, first out. Also, it's very hard to calculate the travel time. The linked list can connect the nodes to another one, but the chain of nodes is also not easy to find the location, and it's time consuming to display. Also, it's hard to display the distance. So the tree is a hierarchical data structure. Generally, there's not one place need to be the top of the hierarchical or the bottom one. So it's very hard to decide how to display the tree. And there is no cycle in the tree, so it's limited the structure or the shape of the tree. Also from the satellite view, it obscured the streets and landmarks below it, so it blocks out a great deal of the view. For the hash table, the rules are internal, so it's not clear to find the rules, and it's very hard to display the distance and calculate travel time. There are many other applications of graphs. First, the Facebook's Graph API, which is the primary way for apps to read and write to Facebook social graph. On the right side of the slides, there is an example showing the Graph API. The Google's Knowledge Graph is another example of using graph to represent knowledge. And it will be efficient for people to find the knowledge they want to know. As we discussed in the class, flight network is another application of graph. The vertices in flight networks are place of departure, destination, airports, aircrafts, and so on. The flight trajectories between airports are the edges, so we can find the efficient route optimization perfectly when using the graph.
Okay, I think we are done with YouTube's part. Also, we have done a lot of research on Google Maps. There are still something we don't know. because they're not public, and we don't know how exactly Google implement Google Maps. But we believe basic concepts of this utilizing location points and routes are very universal. What's different is just their ways to organize geographical data and the different argument for a particular problem. So at the end, we'd like to show you some sample codes. We combine some codes from the textbook and some resources we found on the internet and got this simplified version of how Google Maps is implemented. So first, we need two getters. One is to get the cost of the path, and one is to get the value of the vertices. And then we will go to a more complicated function, which is called get shortest path. In this function, we're gonna use our getter to get the value of the starting point and the end point. And then the textbook gives this function called visit. We don't actually know what it does, but we believe this part is gonna do some traversal and construct the shortest path. And then we can use getter to get the cost of this path and then return this path length. Again, we don't actually know how it works, but we just combine some resources and hope this presentation can give you some basic idea of how Google Maps work. Thank you.